So, factoring a difference of squares. So let's go back to last week when we were multiplying polynomials, and we learned how to do FOIL, where you multiply the first terms, then the outside terms, and the inside terms, and then the last terms. And that's how you multiply two binomials together. So just as a refresher, if we have x plus 2 times x minus 2, we multiply the x times the x, which gives us x squared. Then x times the negative 2, which gives us negative 2x. Then 2 times x, which is a positive 2x. And then the last term is 2 times negative 2, which is negative 4. And then you add your like terms, and in general, the middle terms are the ones that can combine. And in this case, we have a negative 2x plus 2x. Those actually cancel out, and we're left with x squared minus 4. So this result that we got here, this is called a difference of squares. So difference means we've got subtraction going on. And then we actually have two numbers that are, well, not two numbers, two things that are squared. So we have x squared, but we also have 4, which is 2 squared. So we have two squared things that are subtracted. And so that's the difference of squares. And so we're going to be factoring this, which is basically going backwards, taking something where you've got two terms with a subtraction there, they're squared, and then we're going to turn it into the factored form, which is right here. So factoring is basically reversing the multiplication process. It's undoing what we did when we had to multiply. So that difference of squares comes up when you multiply conjugates. And conjugates are the same thing, but they have opposite signs. So the example that we had was x plus 2 times x minus 2. So they're the exact same thing. The only difference is the sign in the middle. They're opposite. And what's special about these is that whenever you multiply conjugates, the middle part always cancels, and you're going to get a difference of squares. And so knowing that anything in this form will always have the middle cancel and always end up in a squares, that allows you to get a pattern or a formula, which then allows you to go backwards. So that way, if you see two things that are squared and they're subtracted, you know what the factored form is going to look like, because it will always end up in conjugates. So our actual formula or shortcut that you can use is a squared minus b squared. And that's like what you see. And then the factored form. So again, this is the factored form, is the multiplication of the conjugates. You basically figure out, well, what was squared? So you're taking the square root, and the square root of those items ends up in your factored form. So if we had a squared, then we're going to have a in the factored form, and then b squared will become b in the factored form. And you just have the same thing, just opposite signs. The key to really being able to recognize the difference of squares is knowing your perfect squares. And perfect squares are numbers you can take square roots of. So like 4, 9, 16, 36, these are all numbers you can take square roots of, and they get whole numbers. So if you know your multiplication really well, then you know your perfect squares, and that will make recognizing that you have a difference of squares really easy. And once you recognize that's what you have, all you need to do is figure out the form, you pop it in, and you can do it in less than 30 seconds. If you've got your, if you really know your multiplication, it's very fast. It's a lot faster than actually going through the factoring process that you would do for like other trinomials. So it's really to your benefit to learn a difference of squares, because it will save you time. And these actually show up a lot in other math problems. So it shows up often enough that this is really to your benefit to kind of memorize this shortcut and recognize when you are in this situation. Now, one thing to be aware of is that a sum of squares, where you have two things but they're added together, that cannot be factored and it's considered prime. Now, when you go on to college algebra, you will learn how to factor it, but that involves complex numbers, but we're not dealing with complex numbers in this course. So just at this point, anything that's a sum of squares is considered prime. So I have a list here of the common perfect squares. So we've got the numbers on the left, and then on the right, the variable version of it. So 1, 4, 9, 16, 25. Basically, if you know your multiplication tables, you know your perfect squares. I have all of the perfect squares on this list memorized except for 14 squared. For whatever reason, that one, I haven't really had to use that one very often, so I've never memorized it, but I've seen 225 and 169 often enough that I have 13 and 15 their squares memorized. The thing you want to know about perfect squares with variables is that it's an even exponent. So you can tell if you have a variable with an exponent, if it's an even exponent, then it's a perfect squared. So here, the perfect squares have even exponents. And basically, whatever's being squared is half the exponent. So if the exponent is 2, then it's square root form, or the thing that's squared is just an exponent of 1, or just x. X to the 4th, it's x squared that's squared, so half of 4 is 2. X to the 6th, half of 6 is 3, so it's x cubed squared. So you're basically, when we're using this formula, we're going to be taking the exponent that's on the variable and dividing it by 2. For the numbers, it doesn't work that way. So you just have to know what your square roots are, or know your multiplication tables, because you're not dividing the numbers by 2. But for the exponents on the variables, you can just divide them by 2. So that's pretty simple. So the hardest part is just recognizing if it's in this form, and that's by knowing the perfect squares. So I've got several different examples here, and I'm going to just go through them and show you kind of the tips, tricks, things you got to look out for. So I'm going to just start by writing the formula for the difference of squares up here so you have something to reference. And I always put a plus b times a minus b, but honestly, the order doesn't matter here because the commutative property says the order of multiplication doesn't matter. So if you want to put your subtraction first, that's fine. It's still the right answer, and it's equivalent. So whether you put the plus first or the minus first, it doesn't matter. It's the same answer. So your key is to recognize that we have a difference of 2 squares. And so you want to kind of rewrite it in the same form where it's something squared minus something squared. So we've got x squared minus 36, and we already have x squared, so it's already something squared. But we can rewrite the 36 as 6 squared. And so that is the key, is to recognize that 36 is 6 squared, and you can rewrite it, and now you have this form. And then once you've recognized the form, it's just a matter of plugging it into the formula. So whatever a is goes into the spots for a, and whatever b is goes where b is in the formula. So you're just recognizing what a and b are, and those are the things that are underneath the square symbol. So in x squared minus 36, when we rewrote it, we have x squared minus 6 squared. So in this case, the location for a that's going to be x, and then what we're going to put in the spot for b is 6. So this factors, and I can even just put in the form with a plus and a minus. So we have x in the front, and then because 36 is 6 squared, it's going to be 6 in the back. And that's your answer. So the hardest part is just rewriting it in the form, but once it's in the form, all you have to do is kind of plug it into your formula and replace, you know, kind of what you have. Sometimes I like to do this sort of without the A and B, but just to think of it as like color coding. And so you've got something that's yellow squared minus, and then let's say we've got something that's, you know, in the spot that's blue that is squared. And then, so if like variables are really difficult for you to kind of see how the formula is, you can use color coding with just kind of some scribbles instead so that you can see how that works. So I could say, okay, this is going to be 6 squared. And so I can change all my 6's to kind of match the color there. And I can even really make try to match it out. I can change all my yellow pieces as white. And so then you can see by color coding the pattern a little bit better. But you can see, okay, what was in front, that's the yellow thing, and then what was in the back, that's the blue thing, and you can really see that pattern. So that's one way that can help you if you're not really good with the variables and plugging things in, is to pay attention to the pattern, and colors can allow you to see the pattern without worrying about what the letters are. So that is the one on the left. It's basically, I mean, a lot of times I skip the step where I rewrite 36 as 6 squared, and I just go straight to the factoring, because in my head I know, oh, 36 is 6 squared, so 6 is going to be that number that I'm going to use. So hold on a moment. My dog is apparently unhappy, and I am going to run out the door, tell my partner in the next room that he needs to go take care of her. So just give me a moment. All right, she probably has to go outside, but I'm busy. All right, so let's look at the example on the right now. So this one is 3w squared minus 300. Now it says to factor completely. Your dog's passed out on the, so at least your dog is quiet and not barking. Because my dog, when my dog is in the car, she will bark and bark and bark. So it's not a pleasant drive. So we've got 3w squared minus 300. And if you look at this, you first want to look at the numbers and say, if I take the square root of these numbers, if I, put in my calculator, use the square root button, will I get a whole number? That's basically how you check that it's a perfect square. Now, in this case, neither 3 nor 300 are perfect squares. But it says to factor completely, and what that means is you always look for the greatest common factor first, and then you proceed with the factoring process. So we always look for the GCF. And so that is, in this case, the largest number that we can divide into 3 and 300, which will be 3. So our GCF is going to be 3. So I'll just write that there. And so what we need to do first is to factor out the 3 before we proceed. So that would be step 2. So I generally do this in my head at this point, but I'm going to show all the steps. So you put your GCF in front, and I'm going to stick my color coding. And then you take what you have with 3w squared and you divide it by the GCF. And then we have a minus, and then we have 300. And we divide it by the GCF. So when you're factoring out the greatest common factor, you're basically dividing it out of your expression, but it's still present, so you still have to put it in front, because it's not, we can't just divide something and have it disappear. You can only do that if you have an equation. We don't have an equation, so it doesn't disappear, it's just getting rewritten. And so it goes in front, we're basically multiplying by 3 and dividing by 3. So that way we're not changing anything, because multiplying and dividing by 3 is basically not doing anything, it's undoing it, but we're rewriting it in a different way. So this would give us 3 times, and then our 3's cancel, so we get w squared, and 300 divided by 3 is 100. So we get 3 times w squared minus 100. And this is where we now have a difference of squares, because we've got a w squared, and then 100 is 10 squared. So step 3 would be to factor the difference of squares. I'm going to just abbreviate that. So we still have our 3 in front, and then I'm going to use my color coding. So we've got w squared minus, and then instead of 100, this is, oops, I want blue. This is 10 squared. Oops. And so now you can see that when we factor and we put it in our form, we're going to have w and 10. So this is going to be 3 in front, and then I like to set up my 2 parentheses, put in my pluses and minuses, and we're going to have w in front, and then 10 in the back. And then that's your factored form. So that would be your final answer. So we have 3 in front, and then w plus 10 times w minus 10. Or you could add the minus part first and do w minus 10 times w plus 10, but either way, the 3 has to be in front. So we have just factored this completely. We first factored out the greatest common factor, and then we had a difference of squares, so then we had to continue factoring. So you're not done after you factor the greatest common factor. You need to look to see if you can continue breaking it apart into different pieces. So these all say factor completely, and so we're going to all have to look, is there a greatest common factor that we can factor out, especially if it doesn't look like it's a difference of squares. So like example on the left here, we have t cubed minus 49t. It's not a difference of squares because we have t cubed, and in order to be a square, it has to have an even exponent, and that's odd. But we can factor out the greatest common factor, which is going to be t. So what you do is we have our t in front, and then I'm going to take t cubed and divide it by 3, or not 3, t. They rhyme, but they're not the same thing. Then I have minus. Then, oh, apparently my dog is still barking. Not very happy right now. Minus 49t, divide by t, and then close the parenthesis. So yeah, we're thinking about this as taking cookies and breaking them into their ingredients. That is basically what we're doing. We're breaking it up into its little pieces, its different parts. When you're multiplying, you're doing the opposite. You're combining them. You're combining all the ingredients together and you get out cookies. Here, we're going in the opposite direction. So we're splitting it apart. So I've got t in front, and then I simplify inside the parentheses. So when I've got a t cubed over t, one of the t's disappears, and that leaves me with t squared. Then with 49 over the 49 t over t, the t's cancel out completely, and we're just left with 49. And then that we have a difference of squares, because 49 is equal to 7 squared. So we can rewrite this. And I always make sure my t's are curved so they don't look like plus signs, because otherwise it can get very, very confusing. So we've got t squared minus, and then that is 7 squared. And so when we use our formula, this is going to become t plus 7 and t minus 7. But we still have to have that other t in front. So I'm going to set this up, my two sets of parentheses, and a plus and a minus. So the t is in the front, and then the 7 is in the back. And so your answer is t times t plus 7 times t minus 7. So we have three things multiplied together, and if you were to go through the multiplication process, that would give you your t cubed minus 49t. So let's look at our 4a squared minus 121b squared. So we've got multiple variables going on here, and these can get tricky for people. But we have a difference of squares because we have a squared, we have b squared, and 4 is 2 squared, 121 is 11 squared. So this is a difference of squares, even if it doesn't really look like it. But we can rewrite it as such. So 4 is 2 squared, and then a squared is a squared, basically. And so the base is 2a, and then that whole thing is squared. So we were learning our rules of exponents, and the rule here when you have a power is that it distributes. So we had our power rule for exponents, where like if you had a, b to the squared, that's a, let's use m. It just, that exponent on the outside distributes. So that'd be a to the m, b to the m. So we're kind of undoing that because we have 2 squared and a squared. So we're undoing the power rule, reversing it, going to the left. So we have something on the right, and now we're going to the left so that we can rewrite this as 2a squared. And it's the same thing with the 121b squared. So these are both things that are squared. So the square root of 121 is 11. And so it's 11 squared and b squared. So that is sort of going to be like in your parentheses. Make that one look straighter. So we have 2a, that quantity squared, minus 11b, that quantity squared. So when you've got these things multiplied together like 4a squared, you can think of squaring or taking the square root of them separately, and then that can get you your base, what's underneath the square. So it looks a little different because it still has, you know, it's got more than one thing, but it's still in this form that I have on the left with the color coding, something squared minus something squared. So it doesn't matter that that something has more than one item, it's still in this form. So when we factor this, let me get my white. Oops. The white and the black pens are right next to each other, and I keep accidentally hitting the black pen. So we have 2a, then that's going to be in the front. And then 11b is going to be in the back. So the hardest part here is just recognizing that while it looks a little complicated because it's got numbers and letters, it's still, these things are still squared. We just have to write it a little differently. And then once you've got it in its form, you just have to, you know, write it with the plus and then write it with the minus. Are there any questions? Okay. So here are some more. You can see I'm kind of getting more complicated here. So on the left, I have 9q squared plus 16. As soon as you see the plus there, it cannot, don't even try to factor because it's not going to be a difference of squares. You might be able to factor greatest common factor out, but you wouldn't be able to go any further than that. And in this case, there's no greatest common factor because 9 and 16 don't have any numbers in common. So all you've got is something squared plus something squared. This is a sum of squares, and sum of squares cannot be factored. So sum of squares cannot be factored, and so we just write prime here because it's a plus, so it's not going to be a difference of squares. So now on the right, I've got a squared minus b to the fourth. So we've got something squared with the a. Now b to the fourth is b squared. Because we go back to that table of perfect squares, x to the fourth is x squared squared. So if you have something in a fourth, then it's a square that's going to be underneath the square. You divide that by 2. So I'm going to rewrite this as we have a squared, which we didn't really need to rewrite as. But instead of b to the fourth, this is b squared. So you divide that exponent by 2, and then that's squared. So now we're in our form, something squared minus something else. So I just set up my plus and my minus. And then I've got a in the front. And then b squared in the back, because it would have been b to the fourth. And so to get to b to the fourth, you need b squared times b squared. So rewriting it really helps you, like rewrite it as something squared minus something squared helps you really see, okay, what are my two things that I need to break it up as? And then you do have to be careful. If you end up with something squared, you have to make sure it doesn't factor further. So like we have this a minus b squared. B squared is a square, but a is not a square, so we can't keep going. But you do have to kind of keep an eye on it and say, oh, did I end up with another difference of squares? Because sometimes you can get multiple difference of squares. So a few more here. Let's look at the one on the left. I have 25 p squared q squared and then minus 1. So we look at this, I've got 25, which is 5 squared, and then we have a p squared and a q squared. So this is a difference of squares. This would be 5p and q squared. 5 squared gives you 25, then you get p squared, q squared. And then 1 is actually equal to 1 squared. So 1 squared is still 1, but it is in this form. So it looks kind of different, but it's still a difference of squares. So I've got my plus, my minus. We've got 5pq in the front, and then 1 in the back. So it's 5pq plus 1 times 5pq minus 1. Now, on the right, I've got one with a fraction, and I know, fractions are kind of tricky for people. And the trick with this fraction thing is we had a rule about the quotient. We had our exponent rules. Actually, let's put that as m, where if you had a division or a fraction inside with an exponent, that it distributes to the top and the bottom. That's what we're going to be doing here, basically, with the 1 over 25. Because 1 over 25 can be written as 1 squared over 5 squared, which then is in this form right here, which means then we can rewrite it as 1 over 5 squared. So this works even with fractions. We have c squared minus, and then it's going to be 1 over 5 squared. Because you can take the square root of 1 and the square root of 25. So you just have to kind of think about, you really need to know your multiplication or your square roots. But now we're in the form. And so we can write it as our factored form, where we've got c in front, and then in the back is going to be 1/5. And yeah, it's going to look kind of gross because you have fractions in there. You have c plus 1/5, c minus 1/5, but it is factored. It was a difference of squares, and this is how it factors. So I've got, these are my last two examples. So this is not a super long one, which is sort of perfect. And we've got 50 minus 32t squared. So if we look at our numbers, 50 and 32 are not numbers we can take the square root of. If you try to do the square root of those numbers, you're going to get decimals. So they're not perfect squares. But we can factor out the greatest common factor. So we're looking for a number that divides evenly into 50 and 32. Let's say I know that 2 goes into both of them. And so then you want to kind of check, is there mentally something bigger? 4 does not go into 50. 5, but does not go into 32. 8 doesn't work. So I think 2 is the largest number that we can actually factor out there. So I'm going to put my 2 in front. And then I'm going to take my 50 and divide it by 2, since I'm factoring out the greatest common factor. Minus, then the 32t squared will be divided by 2. So we simplify inside the parentheses. We leave the 2 on the outside. So 50 divided by 2 is 25. 32 divided by 2 is 16, and then I have my t squared. And now 25 minus 16, t squared, that's a difference of squares, because we've got a perfect square in 25 and a perfect square with 16. So I can take the square root of both of those. So I'm going to rewrite this in their squared form. So 25 is 5 squared. And then 16t, so 16 is 4 squared, and then t to get to t squared. So that's going to be 4t squared. And so when we factor this, we're going to use 5 and 4t. So I have my 2 in front and then my 2 sets of parentheses. My plus and my minus. And so 5 is in the front and 4t is in the back. And so this factors to 2 times 5 plus 4t times 5 minus 4t. Now, a last one here. We have x to the 4th minus 256. So 256 is not on this list of perfect squares. So it's the highest number we have is 225. We don't have 256 on there. So we can take our calculator out and say, okay, what can I take the square root of 256? So you use your square root button, and then you type in 256, and that actually does come out to a whole number at 16. So 16 squared is 256. So my x to the 4th minus 256 is really x squared. Remember, we divide that exponent by 2. So it's x squared minus, and then we're going to have 16 squared, which gives us 256. So I'm going to set up my 2 sets of parentheses. And we have x squared in the front, and then 16 in the back. And I said earlier that if you end up with something squared, you need to look to see if you can factor it further. So we have x squared plus 16, and that is a sum of squares. And yes, we can factor again because we have x squared minus 16. So we need to go further with the x squared minus 16. So if I try to, so our x squared plus 16 doesn't change, that stays the same because that is a sum of squares, that does not factor. But we've got this x squared minus 16, so I can write this as, well, we still got that x squared. And then instead of 16, we've got 4 squared. So we have to factor again. We basically weren't done. We can keep going, and you just keep looking to see if you can keep going. So we have our x squared plus 16. And I'm trying to be very careful to keep all of my color coding the same here. And then we're going to factor our x squared minus 4 squared as another set of parentheses, another difference of squares with a plus and a minus. And so in this case, we have x in front, and then 4 in the front and the back. So we end up with x squared plus 16 times x plus 4 times x minus 4. And we can't go any further. Sum of squares is in the front, the x squared plus 16, that's prime. That cannot factor further. And then once you're left with an x, you can't really break that up anymore. And so this is our final answer. So when we're doing factoring, you're kind of going into our, it's not necessarily, it could be circular. You know, once you factor once, you may be able to factor again. And so you have to keep going, keep going, keep going until you can't go any further. So you need to just keep checking, can I keep going? And if so, you do so. And so when we say factor completely, that's what we mean, is you're not just necessarily factoring once, you're factoring multiple times. You factor as many times as you can until it's broken down as far as it can go. It's sort of like in week 1 when I was showing the factor trees. You know, we would split a number up into 2 branches, and then we would continue splitting each branch up until we couldn't any further. That's the same thing we're doing here when we're factoring. We just keep splitting these things up until you can't. And you can see we're splitting them up into pairs. Just like with the factor tree, we're doing it, split it up into 2 things, and then you keep splitting it up into pairs and pairs and pairs. So we're basically doing the same thing we did with the factor trees in week 1. It's just that those were numbers only. In this case, we have variables involved, but the process is essentially the same sort of thing. We're doing the same process. It just looks very, very different because we've got these variables going on. Right. Could I write? So we've got a sum of squares. I'm not quite sure what your question is. This is a sum of squares, which does not factor. And we don't want to multiply anything back out. So you would just have as your final answer this last step. We don't have anything, like we're not going to write it as like x plus 4 squared because they're not the same. It's an x plus 4 and an x minus 4. So this is literally as far as we can go. We don't need to turn 16 into 4 squared because it's not going to get us anywhere. Because we can't factor the x squared plus 4, there's no point in rewriting 16. So I'm not sure if that fully answers your question there. But this was my last example. So the key to the difference of squares is just being able to recognize you have one, and then once you recognize you have one, it's just figuring out the form and then plugging it in. So it doesn't really involve as much thinking as you might have to do with regular factoring. So I really actually enjoy these things because they're pretty quick. So that's it. That's all I've got. Are there any other questions? All right. So thank you for attending. Really appreciate it.